Okay, welcome to lesson 1-4 about the intermediate value theorem, and this is still part of section 1.4 in your textbook. So to begin, first let's talk a little bit more. You just studied more about continuity of a function continuous at a point. So there are certain types of functions that, because of the way they behave, they are continuous everywhere on their domain. So some of those types of functions include polynomial functions, such as something like f of x equals x to the fourth plus 3x squared minus 8x plus 7. So a polynomial function is going to be continuous everywhere on its domain. And so remember, what that means then is those three different criteria for continuous at a point would apply to every possible value of x in the domain of this function. All right, rational functions are also continuous on their domains. So again, what that means, if I have a function like f of x equals x plus 3 over x minus 1, well, keep in mind, for this particular function, the domain would be x is not equal to 1. So that means this function, x plus 3 over x minus 1, is continuous from negative infinity to 1, and then from 1 to infinity. So at every value in either of those intervals, that rational function is continuous. All right, radical functions are also continuous on their domain, so something like f of x equals the square root of x plus 2. That's a radical function, and that is going to be continuous on its domain. In this particular example, the domain here would be x is greater than or equal to negative 2. Or in interval notation, you could say negative 2 to positive infinity. So for every value of x greater than or equal to negative 2, this particular function would be continuous. And then finally, you've got all of your trigonometric functions. So sine, cosine, tangent, secant, cosecant, cotangent. All 6 of those functions are continuous on their domains. Now, the reason that we care so much about talking about whether or not a function is continuous is that many of the theorems that we're going to learn throughout this course will have some conditions. And in order for those conditions to happen, we have to know more about the functions. One of the most common conditions that we're going to have for many of the theorems moving forward is that we know that the function is continuous on a particular interval. So by knowing in advance that polynomial functions, rational functions, radical functions, and trigonometric functions, by knowing in advance that those are always going to be continuous on their domain, it makes it that much easier for us to recognize when we can apply a theorem, because we know that the condition of continuity is met. Now, what if you're dealing with a function that isn't simply a polynomial, or it isn't simply a trigonometric function? How can we still justify that those functions are continuous? Well, we have a few properties regarding continuous functions that will allow us to make those justifications. So if f and g are both continuous functions, so maybe they're one of the types of functions we just talked about, then the following are also going to be continuous. So the first one we've got is, if you just have some constant c times the function, then the resulting new function is also continuous. So again, that might be something like, taking a basic polynomial, such as x squared. Well, then that means if I were just to do 3x squared, well, 3x squared would also be continuous. So that's all that that's saying. All right, another result that would be continuous, if I took f and I added or subtracted g to that, the resulting function would still be continuous. If I multiply two continuous functions, the resulting function is continuous. Similarly, if I divide two continuous functions, then the resulting function is still continuous, assuming that the denominator is not 0. And then if I compose the two functions, again, that could also be written as f of g of x. So composing two continuous functions also results in a continuous function. So, for example, thinking about that second in particular. If I have f of x is, again, let's maybe just say it's some polynomial x plus 3, and maybe g of x is some trig function tangent of x. Well, if I now have some new function h of x that's actually x squared plus 3 minus the tangent of x, well, this new function, even though it's a very bizarre looking function, it is continuous because it is the result of the difference of a polynomial, which is continuous, and a trigonometric function, which is continuous on its domain. So I would be able to justify that this function h of x is also continuous because it is the difference of two continuous functions. So that's how we can utilize this to justify that we are working with a function that is continuous. Okay, so the reason that we're dealing with, again, all of this idea of continuity for a function is so that we can use this information when we're trying to determine whether the conditions for a theorem are being met, so that we can apply that theorem. And as I said before, one of the most common conditions for the theorems we're going to work with in this course is that we know that the function is continuous on some interval. So this leads us to the first theorem that we're going to talk about here, called the intermediate value theorem. Now this is also abbreviated as the IVT, and this is the first of what we're going to call an existence theorem that you're going to learn in this course. And the reason it's called an existence theorem is it simply gives us justification for how we know something exists, but it doesn't actually specify how you find that something. It just tells us that you can find it because it does exist. So the intermediate value theorem says if f is continuous on a closed interval from a to b, and k is any number between f of a and f of b, then there is at least one number c in the interval a to b such that f of c equals k. Now, a lot of you are probably scratching your head right now, and that's totally fine. So let's show you from a graphing standpoint what this is actually trying to say. So here's what it's trying to say. So if I just have some random function, well, in fact, before I do that, let's point out the different conditions that are being discussed here. So it says if f is continuous on a closed interval, let me use a highlighter instead. So if f is continuous on a closed interval a to b, so that's the first of the two conditions. And then there's a second condition that says k is any number between f of a and f of b. So let's start by talking about that first condition. If f is continuous on the closed interval from a to b. So remember, closed interval, that's referring to the domain. So a and b are values of x. So let's just randomly pick a to be right here and b to be right here. Now, to say that f is continuous on that interval, again, we've got that three-part definition that you just learned in the previous lesson. But from a graphing standpoint, from an intuitive standpoint, all that it means for a function to be continuous is that you can draw it without having to lift your pencil. So if I'm trying to sketch this graph of f, I'm just going to put some random point here, and then now I'm just going to draw whatever graph I want, just as long as it's a function, so make sure it doesn't fail the vertical line test. And there we go. So I was able to draw that. I didn't lift my pencil, so there's no jump in the graph, there's no hole in the graph, there's no asymptote in the graph. It's just starting at this first point on the left, it ends at the point on the right, and it's connected everywhere in between. Okay, so I've now illustrated the first condition. This is some function f, and it's continuous on the closed interval from a to b. Now the second condition says k is any number between f of a and f of b. Now remember, f of a and f of b, those are the y-coordinates. So f of a is actually right here, and f of b is right up here. And it says that k is any number between those. So I'm just going to find any space in between f of a and f of b, and that's going to just be my sample k. All right, so this picture now illustrates both of the conditions for this theorem. So I've got a function f that's continuous on the interval from a to b, and k is some y value between f of a and f of b. What the intermediate value theorem says, if I have both of these conditions met, then there has to be at least one number c in the interval from a to b. So in other words, c, this c right here, that's a value of x. So there has to be some value of c somewhere in the interval from a to b such that f of c is k. So in other words, we want f of c to actually be k. So if I were to find the point on the graph that has a y value of k, then right there must be the value of c that this theorem is guaranteeing that we've got. So that's what this theorem is just saying. So if I can meet those two conditions, if f is continuous on the closed interval from a to b, and k is some number between f of a and f of b, then there has to be at least one number between a and b so that f of c equals k. Okay, so let's look at just a few examples where we utilize the intermediate value theorem. So first, let f be a continuous function with selected values shown below. So here we just have a table where they've given us some specific values for the function. Explain why there must be at least one value of x for which f of x equals -1. So a couple of things to point out here about the question. First, notice that it's not asking us to find anything. It doesn't say solve for x. It doesn't say, anything about involving solving. It's asking us to show that there has to be something existing. And that's the key that you want to look for in questions that might indicate to you to think about theorems like the intermediate value theorem. Okay, so I'll mention that as we go through this course, but again, keep in mind that there are certain keywords you're going to want to look for to indicate that you should be considering these existence theorems. Okay, so since right now the only existence theorem that you know is the IVT, that's what we're going to try to work with. So notice, we do already know that the function f is continuous because they told us. So we're going to state that. So in order for us to try to use the intermediate value theorem in any kind of a justification, our very first task is to show that the conditions for the theorem are even met. So the first thing I'm going to do is talk about those conditions. So first, we know that f is continuous. Okay, so right there, that takes care of the first of the two conditions. Now, given in the theorem itself, we talked about f being continuous on some closed interval. For this example, notice they just said f is continuous, the implication meaning that it's continuous everywhere. Well, if this function is continuous everywhere, then that means it's going to be continuous on some specific interval within all real numbers. Okay, so we don't have to get overly concerned about that. The fact that we know f is continuous everywhere, that takes care of that. All right, the second thing, remember the second condition, is we were looking for some y value of mention. Notice right here, they are talking about proving that there's at least one value of x for which f of x equals -1. So -1 is that value of k that we're talking about. So we want to show that -1 is between some f of a and some f of b. So when I'm scanning these function values, down here, I notice that -1 is between -7 and -2. So I can now say that -1 is between f of 5, which is -7, and f of 7, which is +2. So I've now stated the second condition for the intermediate value theorem. So therefore, I don't know if you've seen it before. These 3 dots kind of in a triangle, that's a shorthand way of saying therefore. And I encourage you to use the same thing. So therefore, and here's the key, you must state this. Therefore, by the IVT, you have to state by the IVT. You cannot leave that out. Because by stating the name of the theorem, you're letting the theorem do the rest of the heavy lifting for you in terms of this explanation. Okay? So we had to state that the 2 conditions were met so that we could then state that the theorem does the rest of the work for us. So therefore, by the IVT, there must be at least one value of x for which f of x equals -1. Specifically, that value of x would be in the interval from 5 to 7. All right, so that's an example of how we might use the intermediate value theorem. Let's look at another. Okay, explain why the function has a 0 in the given interval. And the function we're dealing with here is f of x equals x squared minus 1 minus the square root of x. And we're talking about on the closed interval from 0 to 4. So again, notice they're just asking us to explain why the function has a 0, why some 0 exists. Also, if you're not quite remembering, when we talk about the 0 of a function, we're talking about the x value that makes the function's y value equal 0. So right here, when they talk about having a 0, that's really talking about k being 0, k from the theorem. Okay, so again, that means I'm going to try to use the intermediate value theorem to prove that there must be some value in the interval from 0 to 4 so that f of c equals 0. Okay, so in order to use the intermediate value theorem, once again, I need to verify that the 2 conditions for the theorem are met. So first we have to talk about continuity of this function. So this is what I was referring to a little bit earlier. This is definitely a unique type of function. It's not simply a polynomial, it's not simply a radical, it's a combination of the 2. But in fact, it's actually a polynomial minus a radical. And as we saw earlier, if I take 2 continuous functions and I simply subtract them, then the resulting function is still continuous. So I can justifiably say that f is continuous on the closed interval from 0 to 4. Now notice this time I'm stating a specific interval, unlike the previous example, because on this example we are discussing a specific interval already. Okay, so we're specifically trying to prove that the 0 exists on this interval, so we're focusing exclusively on that interval. All right, so f is continuous on the interval from 0 to 4. Now, remember the second condition, we have to show that the number 0 is between f of 0 and f of 4. So in order to do that, we're going to actually find those values. So f of 0, well, that's going to be 0 squared minus 1 minus the square root of 0, which is -1. And then f of 4 is going to be 4 squared minus 1 minus the square root of 4. That's going to be 16 minus 1, which is 15, minus 2, which is 13. So now we can see that f of 0 is -1, f of 4 is 13, and clearly we can state that 0, which is our k, is between f of 0 and f of 4. So 0 is between f of 0, which is -1, and f of 4, which is 13. So now I have stated that both of the conditions for the IVT are met. So now I can say, therefore, there's my 3 dots again, by the IVT, once again, you have to state the name of the theorem or you have not completed your argument. So therefore, by the IVT, there must be a 0 on the closed interval (0 to 4). Okay, our last example here. Verify that the IVT applies to the indicated interval and then find the value of C guaranteed by the theorem. So the only real difference here is that not only are we trying to show that the IVT applies and then make the conclusion from it, but now we're actually trying to find that value guaranteed by the theorem. Okay, so we're still going to start the same way. It says verify that the IVT applies. That means we need to make sure that the two conditions are met. Well, the function that we've got here is clearly just a polynomial, so we can definitely say that f is continuous. Now, it's a polynomial, so we could say that it's continuous everywhere, but remember, we have to be specific to the interval talking about here. So f is continuous on the closed interval (-3 to 0). So first condition is met. Now remember, the second condition, we have to make sure that k, which in this case is 7, is between f of a, which is (-3, a is (-3), and f of b, where b is 0. So let's find f of (-3) and f of 0. So f of (-3), well, that's going to be (-3 squared minus 4 times a (-3) minus 5. That's going to be a 9 plus a 12, so that's 21, minus 5, which gives us 16. F of 0, well, that's just going to be 0 squared minus 4 times 0 minus 5, and that's just going to be (-5). And it's very clear then that 7 is definitely between f of (-3) and f of 0. So therefore, the IVT applies. So there exists at least one value C in the closed interval (-3 to 0 such that f of C equals 7. Okay, so we've now shown that the IVT does apply to this function on this interval for that value of k. But now it says to find the value of C guaranteed by the theorem. So in other words, now they're just asking us to do some algebra. And that means we're trying to find for what value of C does f of C, which would become c squared minus 4x minus 5, for what value of C, that's a C. So for what value of C would that function equal 7? So really, we're just looking at this equation right here. So let's just solve that. So c squared minus 4c minus 5 equals 7. It's quadratic, so I'm going to subtract the 7 from both sides, and I've got c squared minus 4c minus 12 equals 0. I can factor that. By the way, if you do leave them with x's instead of c's, it's fine. It's not that big of a deal. So I've got c minus 6 and c plus 2. So remember, now if I set each of those equal to 0, I'm going to end up with c equals 6 and c equals (-2). Now, that's two values. Remember, the theorem says there has to exist at least one in the interval. Here's the problem. Remember the interval that we're talking about here. We're talking about the interval (-3 to 0. Are both of these values of c in that interval? No, c equals 6 is clearly outside of that interval, so that value is not one of the values that we were discussing that's guaranteed by the theorem. However, c equals -2 is in the interval. So c equals -2 is the only value that we should be stating that was guaranteed by the intermediate value theorem for this interval. All right, and that is the intermediate value theorem. So remember, this is an existence theorem. Its key purpose is to allow us to justify the existence of something. In order to use this theorem, first you need to make sure that you've verified that the conditions are met, and then make sure that you invoke the name of the theorem in your conclusion. The name of the theorem itself does the rest of the heavy lifting for you.